This is my implementation of the asymmetric encryption algorithm RSA. The program is split into two classes. This first class is the main class and manages the UI. The second class over here, RSA Toolkit, contains all the functions that are actually a part of using RSA. Firstly, we have some utility functions which count such as functions which count items in an array, functions which calculate a modular inverse, which is important in generating keys for RSA. This is the initialization function that is called every time you create a new RSA toolkit. This is a function for calculating a least common multiple. A subfunction of that is this one, which calculates the GCD, or greatest common divisor. This is a function that, well, air quotes, generates one of many prime numbers. It's really this rather large list that I'm not about to scroll through the entire thing because it contains all the primes between 17,000 and 104,000. It selects a random prime from this list and returns it. This is the function that actually generates the keys used in RSA. The security in RSA is derived from the fact that given two very large prime numbers, these are not large enough, but this is mostly just a proof of concept, that given two very large prime numbers multiplied together, it is very difficult to get those prime factors out again. So thus, this function takes two prime numbers, then multiplies them together to create what's called the modulus factor. Then it calculates, using the prime factors of the modulus, it calculates the totient of the modulus. Then we select a random integer e that also happens to be coprime with this totient. 65537 is a value that just happens to be used all across the industry, so that's the value we will use here as well. Then we calculate the modular inverse of both of e and the totient. That's this function back up here. And this generates our private key, which is what we use to decrypt. Then we set these Boolean variables to true to let the rest of the program know that we now have a public key and a private key. And then because the totient is actually is a very dangerous variable in that it can be easily used to crack the encryption, we then set it to 0 to discard it, so that it can't be extracted. This here is another definition of the generate keys function in case that doesn't take the prime numbers, just so that for the ease of use. The next set of functions are actually used in the encryption and decryption. This function here will take a provided string, this variable str, and break it up into an array of 3 character groups. This is important because what we do to encode a string with RSA is we take the string, we break it up into 3 character groups, then UTF-8 encode each individual character, then convert the byte from that character into an integer, which we then append to each other to create a 9-digit number representing the 3-character sequence. That whole mess with UTF-8 is this function right here. So this function here is a little wrapper for this function and this function, combining them to take a provided string and output it in an array of longs, which are just larger integers. We don't need to use longs in this program, but I consider it better to use longs just so that we have the space and because modern computers generally have the memory. This is the set of functions used for encrypting. This next set of functions is used for decrypting. This first function takes a long of the format created by this, which is three integers appended to each other, where each integer represents a UTF-8 encoded character. It takes this long, breaks it back up into the three integers, then converts the integers back into characters, and returns the characters. This function serves as a convenient wrapper for this, taking a long array and parsing it back into the string that it came from. It is the inverse function of this function. This function right here is probably the meat of this whole library. This function and the one after it. Because these functions take the generated keys from earlier and use them to encrypt and decrypt the strings. This one will encrypt a string. This function here encrypts the string and returns it as a long array. It does this by first breaking up the provided string into a long array using the functions up here, then performing the RSA operation on each long. The RSA operation is simply taking the public key exponent E, in this case 65537, raising the number you wish to encrypt, which right here is B, to the exponent E, then running it through modulus in. This sequence of operations will give you the encrypted value. This encrypted value then can be sent off to the person who has the private key, which is then decrypted by doing the same operation except with the private key exponent instead of the public key exponent. Finally, we have a set of functions that are used to manually set the public and private keys from outside the library instead of just generating them. There's also a set of functions to get various variables inside the function, such as what the private key is, what the public key is, what the primes used to generate the private and public keys are, or just a general function that returns all of the keys. The UI is a command line based interface with an inbuilt password system as well. Of course, first we have a few utility functions that count the number of items in an array, and another utility function that is used for comparing two arrays. Here in the main, the first thing we do is we create a new RSA toolkit, which we then use for all the decrypting and encrypting operations later, and we create a scanner to scan. We create a scanner for the purpose of scanning user input and getting a password. Then there's a long array here, which is a secured version of the password. You cannot immediately read this password off of the code. However, if you knew how it was encoded, which is fairly simple, you would be able to easily crack the password. Next, we have this switch case, which reads the arguments passed to the function. The reason why we do this switch case is so that the arguments can be passed to the function in any order. It does not. Next, we have a system that tests if you provided the -- help argument, which just displays a little help menu explaining exactly what each argument does. If you didn't provide the -- help argument, then we go through this little system, which gives you 3 chances to correctly enter the password to the program. If you fail to enter the password to the program, it exits. But if you succeed, it moves on to this subsystem. This subsystem first checks if the -k option was provided. The -k option is used when you are trying to provide a key that has already been generated. If the -k option is provided, it finds out what the argument after the -k option was and splits it into an array, into an array based off of the format provided here, which would be exponent modulus, split up with the vertical line character. It then parses the it then parses the it then checks it first checks if you actually provided the -kp argument, which means that you provided prime numbers instead of an exponent modulus, but in the same format as the exponent modulus. If you did provide the kp argument, it then goes and calls the generate keys using the provided primes. Do note that the function does assume that the numbers you provide are prime numbers. If they are not prime numbers, then it will break the RSA encryption. Then you will not be able to encrypt and decrypt. If you did not do the KP option, then it first checks if you provided the decrypt option. If you provided the decrypt option, it sets the key as the private key, because the private key is the key you would need in order to decrypt. If you provided the encrypt option, which is E, then it would set it as the public key. However, if you did not provide the -k option in the first place, then it simply generates a fresh set of keys. This segment of the program is used for the actual encryption and decryption part of the UI. First, it detects if you provided the -d option, and if you provided the -d option, it parses the string the string provided by the arguments into a long array, then passes that long array into the RSA decrypt function, and stores the result. If you provided the -e or encrypt option, then it simply takes the string provided by the arguments and encrypts it using the RSA encrypt function. This final section here is used for returning information to the user. The first information it returns is the keys it used for encrypting and decrypting. The next set of information it provides is the unencrypted string, regardless if you were decrypting or encrypting the string. The final piece of information is the long array, delimited with the vertical line character, and thus ends the program.